So this is the second part of liver physiology, where I'm going to focus on metabolic and detoxification roles of the liver. So before I talk about the metabolic and detoxification processes, it's also worth remembering an important physiological function related to metabolism are the endocrine functions of the liver. And the liver produces many hormones into the bloodstream. It also forms and secretes angiotensinogen, which is a very important protein because that protein is a precursor to hormones angiotensin 1 and angiotensin 2. And while we will cover some of the roles of angiotensin 1 and angiotensin 2 in terms of physiology, it's worth bearing in mind that these hormones originating from the liver in terms of angiotensinogen are highly important in regulation of your fluids, your salt balance, your blood pressure as well. Also, the liver has endocrine formation or roles in iron metabolism. And iron, we've already spoken a little bit about its recycling, but when metabolized heme is returned to the plasma, it binds to transferrin, and iron is also stored in the liver as ferritin. And hepcidin, again a hormone formed in the liver, is secreted into the blood, and that's what endocrine hormones do. They are secreted into the blood like angiotensinogen, and they control that iron uptake from the liver. So low levels of hepcidin increase uptake of iron, high levels reduce iron uptake. So in terms of energy metabolism, well, carbohydrate metabolism is covered in detail by Dr. Cottrell, and that will also cover glycogenesis, and glycogenesis occurs when you have increased insulin, and that stimulates storage glucose as glycogen. Glycogenolysis, where we have falls in plasma glucose, they stimulate glucagon converting enzyme to convert glycogen to glucose. And also in some extreme cases, you can have gluconeogenesis, which is the formation of glucose from non-carbohydrate sources, such as amino acid, glycerol, and lactate. And it's in the liver that you get the actual formation of the glycogen and the breakdown of glycogen and gluconeogenesis as well. Probably more important than, or as important as its role in energy metabolism, is the metabolic production of plasma proteins. And most proteins in the blood plasma are synthesized in the liver. A couple of important, or a few important ones I want to mention are albumin, which is the major protein constituent in the plasma, and that's responsible for osmotic pressure, and reductions in osmotic pressure can cause fluid retention around organs and tissues. Albumin is also a really important protein for binding of drugs, which we'll learn about more next year. And drugs binding to albumin can affect the levels of drugs and other circulating lipids, etc., in the blood. Liver also produces globulins, and these globulins are proteins that are really important for both lipid and vitamin transport, as well as antibody generation. So you can see the liver's having roles in nutrition there, as well as immunity. And finally, most of the clotting factors, which you will learn about in other lectures, not provided by me, are also produced by the liver, and they're the factors, the proteins that help your blood to clot. They are mainly produced by the liver as well. And talking about all these proteins being produced by the liver brings us round to talking about a role of the liver that many of us are already familiar with, and that's the role in detoxification. And one of the primary primary functions of the liver is to protect us from ammonia produced by protein metabolism. So when proteins are catabolized around the body, they form this harmful urea, and urea is highly toxic. So the very process of metabolism itself is toxic, and this is where the liver, via the urea cycle, forms urea, where the urea is a less toxic form, which is then excreted into the blood and then excreted from the body by the kidney in the urine. Now, what's happening here is ammonia is combined to form carbamyl phosphate, so it's conjugated to form carbamyl phosphate, and that carbamyl phosphate in the liver is then metabolized to form citrulline. It is then conjugated to form arginosuccinate, and arginosuccinate is then cleaved to form arginine, from which we produce urea, the less harmful product, and that's excreted in the blood plasma. And that brings us to the idea of how, and talking of protein metabolism and detoxification of ammonia, brings us to the liver's role in detoxification processes. And as well as the breakdown product of protein metabolism, ammonia, the liver also metabolites lots of endogenous hormones, for example, insulin, glucagon, and corticosteroid hormones in the body. Probably, though, the most familiar metabolic pathway is the metabolism of drugs and poisons. It's one of the major functions of the liver is to process and remove xenobiotics, which include drugs. They're the things not normally produced by your body and could be potentially poisonous to your body. So your liver wants to get rid of those xenobiotics from outside your biology. That process is what we call biotransformation. We've already seen that biotransformation in ammonia conversion into urea. And this normally occurs via phase 1 reactions, where enzymes cause oxidation, reduction, and hydrolysis type reactions to take the drug or the toxin or whatever it is into a modified form, where it then enters into phase 2. In terms of ammonia production, we've already seen that, where ammonia is reacted with to form carbamyl phosphate, which is the modified product, which is then undergone further phase 2 reaction. Now, phase 2 reaction is normally the conjugation of the functional groups. In other words, it tends to be conjugated with glucuronic acid, sulfate, or acetate. There are other ways of conjugation or joining together, and that forms the drug conjugate. And then it's the drug conjugate. Sometimes that undergoes further metabolism as well, but it's normally the drug conjugate that is both inactivated form, but also easier to be excreted. So to give a case study of detoxification, it's probably the one that most of us are familiar with, is detoxification of alcohol. And that also brings us to how alcohol can cause liver damage. So alcohol, or ethanol, is oxidized to acetaldehyde. So what we're showing here is the square is meant to represent a liver cell, and ethanol, which has been ingested from the blood, is metabolized by alcohol dehydrogenases. Now, alcohol dehydrogenase is an enzyme and can only process small amounts of alcohol. So it's when you drink alcohol, the increase in alcohol concentration in your blood is what makes you feel drunk. And slowly, as the alcohol is metabolized, you begin to sober up because that alcohol is being metabolized by your liver, but it's rapidly overloaded this process. So that forms acetaldehyde. Acetaldehyde is then conjugated and we form acetic acid. And it's the acetic acid that is then removed into the circulation, where it's then excreted by the kidneys. So the main thing to notice about this process is each step of this process produces what we call reactive oxygen species. So in the process of eliminating and biotransforming the alcohol, it actually produces reactive oxygen species which can cause inflammation and damage to the liver. And this occurs with other drugs that are detoxified by the liver as well. They can also cause damage to a greater or lesser extent, but alcohol in particular is one that causes damage to the liver because it produces lots of reactive oxygen species and damages the liver. But the liver is resistant to alcohol damage because it's able to regenerate. Okay, so if it receives a little bit of damage, the liver is able to regenerate on its own. It can produce more hepatocytes quite rapidly, and it can remain functional. However, if you have chronic and repeated heavy drinking, what can happen is that with chronic and heavy drinking, the rate of damage starts to occur at a rate that exceeds the liver's ability to regenerate itself, and that can end up to causing liver damage.